So intersection, uh, for example, A is a set contains 1, 3 and 9. B is another set contains suppose 3 and 5. Now what will be A intersection B? So A intersection B will be common element, that is 3. Now set difference. Set difference. We can define set difference as A notation like minus A minus B, in that way set difference X such that X belongs to A and X does not belongs to B. For example, A is a set contains 1, 3 and 9. B is a set contains 3, 5. Now A set difference of B is basically 1, comma 9. X element will be like that. X belongs to A means 1 belongs to A, and that element should not belongs to B. 1 does not belongs to the set B. Similarly, 9 belongs to set A, but it does not belongs to the set B. Now, two laws will be required. We know it is a De Morgan's law. De Morgan's law. One, A union B whole bar is equal to A union intersection B bar. Number two, A intersection B whole bar is equal to A basically these are a complement, A complement union of B complement or bar. Now disjoint set. Disjoint sets. If we can define, if A and B have no common element, no common element, that is A intersection of B will be this empty. Then we say A and B are disjoint. Now cardinality. What is cardinality? Cardinality of a set, cardinality of a set A written as this notation is the number of element in set A. Now power set. What is power set? Power set. Uh, it can be defined as uh, set of all subset of A. If A is a set, and then set of all subset of A will be called the power set. So the power set of a set A written of this is the set of all subset of A. That is a set containing n elements has a power set containing 2 to the power n elements. For example, given A, set A 1, 2, 3, and suppose we have to find power set of A. As the set contains three elements, three members, 1, 2, and 3. So the power set will be defined as 2 to the power the number of elements in the set A. That is, uh, the power set P of A contains 8 elements. That is, 2 to the power n is the formula. N elements. If it has n elements, then power set will contain 2 to the power n number of elements. So 2 to the power, as it contains 3 elements, so 2 to the power 3 is equal to 8. So P of A, power set of A, will be written in that way, set of all subsets. So we can write the empty, then all the members 1, set 1, 2, 3, then 1, 2, then 1, 3, then 2, 3, and finally 1, 2, and 3. So set of, so how many elements in the power set? 1, 2, 3, 4, 5, 6, 7, 8. So uh, set of all subset of A is basically the power set. Now uh, the Cartesian product. Cartesian product. How we define it? Let A and B be two set. Then set of all ordered pairs. Then set of all ordered pairs is x, y, where x belongs to A and Y belongs to B is called Cartesian product of A and B. Cartesian product of A and B. For example, suppose A cross or formally we can define in that way, uh, x comma y, this is the ordered pair where such that x belongs to A and y belongs to B. And now we'll give an example. Suppose the uh, uh, set A contains two elements 1 2, and the set B contains three elements, suppose x, y and z, and C contains element, suppose 3 and 4. Now what will be the Cartesian product of A cross B cross C? So what will be the Cartesian product of A cross B cross C? Or simply we just remove this, not necessary, only A cross B. So we can write in that way. This is a set, it is 2 for set A, and for B, set B it will be x, y and z. Similarly it will be x, y and z. So the ordered pair will be like that: 1 x, then 1 y, then 1 z. 2 x, 2 y and 2 z. Yeah, so it is an ordered pair. So this is the Cartesian product of A cross B. Now relation. What is relation? Uh, we can define, suppose S and T are the two set. So a relation on set S and T is a set of ordered pair S and T. So two set S and T is a set of the ordered pair S of T, a relation. For example, a binary relation, suppose row between S and T is a subset of S cross T. If ordered pair S T belongs to this relation row, then element S of the set S is said to be related to T of the set T by the relation. By the relation, obviously it will be rho. Suppose these two sets are like that. We have two sets. Suppose this is a S and it is a T, and the members are suppose A, B, C, D, and E. Here the members are like W, X, Y, and Z. And suppose the A is related to Y and C is related to W and C is also related to Z and D is suppose related to Y. Okay. So it is called domain and it is a range. Okay. So set of all first element and it is a set of all second element. Now we can define a domain like that. Domain uh, domain of the relation row can be defined in that way is A element A such that A belongs to the first, that is set S or A, and AB belongs to the relation row where A is a member. We assume that A is a member of the set. It is a set, and B is a member of the set B. We assume that B is a set B. Here B is a set member of the set B. Similarly, we can define the image, or we can say the range. So image uh, Im and the relation is row can be defined as B such that B belongs to B and AB belongs to the relation row. Clear? So this is a domain and this is basically the its image. And if this uh, relation exists, so relation row can be defined as this is an ordered pair, obviously ordered pair. So A relates to Y, so A comma Y, then C relates to W, so C comma W. C also relates to Z, so C comma Z, and D relates to Y, D comma Y. So this is basically the relation row. It is a binary relation. We will give another example. Suppose uh, another example. Let A be a set having elements 2, 3, 5, and 6. And B is another set having elements 8, 10, 13, and 20. And row means relation is defined as row is defined as A relates to B if and only if and only if A is a divisor of B for A belongs to the set A and B belongs to the set B. So now what will be the relations? So now rho will be like that. 2 will be divisor of 8. So there will be a relation 2 comma 8. Similarly 2 comma 10. Similarly 2 comma 20. Similarly 5 comma 10 and 5 comma 20. So these relations are exist. So in this relation, domain of relation rho is basically 2 and 5, and image of the relation rho is basically 8, 10 and 20. Now we'll define equivalence relation. Equivalence relation. Uh, Equivalence relation can be defined. Suppose A subset R, A subset R is a subset of A Cartesian product of A is called an equivalent equivalence relation on A if R satisfies the some properties satisfies these following properties or following. What are the properties? A A comma A belongs to the relation R for all A belongs to the set A. And we call in this scenario R is reflexive. So reflexive is a property. Second, if so A comma A belongs to the relation R for all A belongs to the set A. Then we call R is reflexive. And if A, B belongs, this order pair belongs to the relation R, then B comma A also belongs to the relation R. If this property is satisfied, then we call R is symmetric. We call R is symmetric. And third property, if A, B belongs to the relation R, B comma C belongs to the relation R, and it will be and if these two relations A, B belongs to the relation as well as B, comma C also belongs to the relation R, then A, comma C belongs to the relation. Then we call R is transitive. Clear? So then we say that the relation R, if the relation R satisfies these properties, then we call R is a equivalence relation. For example, I give some example. Suppose a set A contains some members or element 0, 1, 2 and 3. And suppose the relation R1 is like that 0, 0, comma 1, comma 1, comma 2, comma 2, comma 3, comma 3. And another relation R2 is like that 0, comma 0, 1, comma 1, 1, comma 2, 2, comma 1, uh, 2, comma 2, comma 3, comma 3. And another relation 0, comma 0, comma 1, 1, comma 3, 2, comma 2, 2, comma 3, 3, comma 1, 3, comma 2, 3, comma 3. Now, among these relations, which of the relations are equivalence relations? Now come to the relation R1. 0, 0, 1, 1, 2, 2, 3, 3. These are basically satisfies the first property, that is for all A of the set A, for all 0, 1, 2, 3, all the elements of the set A, this 0, 0, 1, 1, 2, 2, 3, 3 is are basically reflexive properties. So A, comma A belongs to the relation R1, that is reflexive property satisfied. So obviously R1 is an equivalence relation. Similarly, the relation R2 0, 0, 1, 1, 2, 2 and 3, 3. All these are satisfied the reflexive property, and 1, 2 satisfies AB. AB belongs to relation R, then BA should be relates to the relates to A, BA order pair should be in the relation. So 1, 2, similarly 2, 1. So these two basically satisfy the symmetric property. So all this ordered pair satisfies reflexive properties as well as symmetric properties. So obviously R2 is also an equivalence relation. Now come to the relation R3. Here 0, 0, 1, 1, 2, 2 and 3, 3, all these are satisfied the reflexive property. Also 1, 3 and 3, 1. Look here, A, B, B, A. This and this satisfies the symmetric property. Similarly 2, 3, 3, 2 also satisfies the symmetric property. Now point is 1, 3. Now the point is 1, 3 and 3, 2. 1, 3 and 3, 2. These are basically AB. We call it as AB, and 3, 2 means it is a BC. We can say another member is C. So AC should be in the relation. AC means 3, 2 should be in the relation. sorry, not 3 2, 1 AC. A means 1 and C means 2. 1 2. 1 2 should be in the relation, but 1 2 does not belong to this relation. So R3 is not an equivalence relation because 1 3 present and 3 2 present, but 1 2 is not in R3. So that is no transitive property satisfied by relation R3. Hence, it is not equivalent. So it is a equivalence relation. It is equivalence. It is not an equivalence relation. Now we can define another uh, terminology, that is a partial order relation. Partial order relation, and it can be defined a relation a relation R on a set A is called partial order partial order if R is, as we have defined, it is reflexive, B antisymmetric. In case of uh, uh, equivalence relation, it was a symmetric, but here it is a antisymmetric. Antisymmetric. Antisymmetric, and C transitive. Now, this antisymmetric means basically if order pair AB belongs to the relation R and order pair BA belongs to the relation R, then A equal to B must hold. This is basically the antisymmetric. Another example we can say for this, we assume that N is basically set of all natural number, clear? And suppose the order pair x comma y belongs to the relation R, and we define y is divisible by x for x and y belongs to the natural number n. So now in this scenario, AB, if AB belongs to the relation R, it means B is divisible by A, divisible by A. Now B comma A belongs to the relation R. Clear? Here xy belongs to relation R, and basically relation is defined in that way. Xy belongs to the relation R only if y is divisible by x. Second element will be divisible by the first element. So A B belongs to relation R, we can say that B is divisible by A, and B A belongs to relation R means A is divisible by B. And when these two things will be satisfied, it is possible only, it is possible when A is equal to B. Okay, so this is the partial order relation. Now we give another uh, principle of mathematical induction which will be required in some cases in theory of computation for some proof. So now principle of mathematical induction. Principle of mathematical induction. Yeah. So what is this? Let P be a property of positive integers such that one, what is the base case? P of 1 is true, and induction or inductive step if P of n is true, then P of n plus 1 is true. Then P of n is true for all positive integers. Now this P of n in the step is basically called the induction hypothesis. So the premise P of n in the inductive step is called induction hypothesis. So now the base case states that the of 1 P of 1 is true, then the inductive step implies that P of 2 is true, P of, now again by the inductive step we see that P of 3 is also true, and so on. So consequently the property must be true for all the positive integers. Like that, P of 1, then P of 2, and so on. Then P of n, this is the inductive state, and then we prove P of n plus 1, it is also true. It is true. And by using these inductive steps, you can say that P of n plus 1 is true, and P of n is basically the assume that it is true for n, then we have to prove that it is also true for P of n plus 1. Now we'll give an example for example. Uh, Suppose we have to prove prove that the sum of the n first odd positive integer integers is n square. We have to prove this. That is, we can write in that 1 plus 3 plus 5 plus 2 of n minus 1 is equal to n square. We have to prove this by using the principle of mathematical induction. So how we can prove this? So solution will be, we assume, let we have s of n equal to 1 plus 3 plus 5 plus 2n minus 1. And we have to prove that for every positive integer n, we have to prove that for every positive integer n, s of n is equal to n square. For every positive integer, obviously first odd positive integer s of n is equal to n square. Now, base case, what is base case? N equal to 1. So if n equal to 1, so if we put in this relation, so we'll obtain s of 1 is equal to 1, which can be written as 1 square. So it is true for base case. 1 n equal to 1 is a base case, so it is true. So the property is true for n equal to 1 or for 1. Now, inductive step. Inductive step, we assume, that is the induction hypothesis, assume that the property is true for some positive integer n, that is s of n is equal to n square. We must prove that it is also true for n plus 1. So we must prove that it is also true for n plus 1. That is, s of n plus 1 is equal to n plus 1 square. Now, s of n plus 1 can be written as 1 plus 3 plus 5 plus 2n minus 1 plus 2n plus 1. We put n is equal to n plus 1 in the last term, 2n minus 1 plus 2n plus 1. Okay. Now, it will be like that. This from this term, it will be s of n, and remaining term is 2n plus 1. Now, s of n, we assume initially that it is a n square. In case of induction hypothesis, we assume that it is a n square. So, n square plus 2n plus 1, which is basically n plus 1 square. Clear? So, the property is true for all integers. So, in this way, by using induction hypothesis, we can prove